You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Parameter-efficient tuning refers to a class of methods that adapt very large language models without retraining every one of their billions or even trillions of parameters. The essence of the idea is economy. Identify where small, strategic changes can yield significant improvements, rather than attempting to overhaul the entire system. Imagine trying to retune a grand piano. One option would be to replace every string and hammer, which would be costly and unnecessary, while another would be to make small adjustments to only the notes that have drifted out of tune. Parameter-efficient tuning mirrors this second approach. It adds or modifies a small set of additional components so that the base model can be reused again and again with minimal expense. This not only reduces the hardware requirements, but also preserves the stability and general knowledge of the original pre-trained system. In an age where frontier models contain hundreds of billions of parameters, such methods transform fine-tuning from something only giant corporations could afford into a strategy accessible to research groups, smaller companies, and even individual practitioners. Full fine-tuning, in contrast, has historically been the standard for adapting models. In full fine-tuning, all of the weights in a model are retrained on a new dataset to achieve task-specific performance. While this provides the maximum flexibility, it comes at a tremendous cost. Training runs can require clusters of advanced GPUs operating for weeks or even months, consuming enormous amounts of electricity and incurring financial burdens that reach into millions of dollars. Beyond training, storing a fully fine-tuned model for each task also becomes impractical, since duplicating the entire weight set produces massive memory demands. Each version may take hundreds of gigabytes of storage, making it infeasible to maintain multiple task-specific models. Moreover, researchers began to realize that retraining every parameter was unnecessary. Many weights encode general linguistic knowledge that transfers well across tasks, and only a fraction need to be adapted. The inefficiency of full fine-tuning, combined with the rapid growth in model size, created the motivation for parameter-efficient alternatives that target the right places without wasting resources. Low-rank adaptation, known as LoRa, is one of the most widely used parameter-efficient methods. LoRa is based on the observation that weight updates in deep networks often have a low-rank structure, meaning they can be represented compactly without needing to touch the full matrices. Instead of directly modifying the enormous weight matrices in the model, LoRa inserts additional low-rank matrices that capture the fine-tuning adjustments. These matrices are small and efficient to train, while the original model weights remain frozen. When the model is used for inference, the outputs from the frozen weights and the LoRa updates are combined, producing a response that reflects both the general knowledge of the pre-trained model and the task-specific modifications learned through LoRa. This approach has proven remarkably effective, delivering results nearly identical to full fine-tuning, but with only a fraction of the training burden. LoRa has quickly become a standard tool because it bridges the gap between efficiency and performance in a way that scales with modern models. Understanding how LoRa works can be explained with a simple analogy. Imagine you are editing a massive book, but only want to add footnotes in certain places instead of rewriting entire chapters. The book remains intact, but the footnotes provide context and corrections specific to your needs. LoRa works the same way. It leaves the large weight matrices of the pre-trained model untouched, while inserting smaller low-rank matrices that function like footnotes, capturing targeted changes. During fine-tuning, these smaller matrices are updated, and they add subtle modifications to the output of the original weights. This strategy drastically reduces the number of parameters that must be trained, often by orders of magnitude, without discarding the knowledge encoded in the pre-trained model. It is a clever compromise between the stability of frozen weights and the flexibility of adaptation, giving researchers a way to create specialized models while reusing the heavy investment already made in pre-training. The benefits of LoRa are substantial and multifaceted. First, it reduces computational costs by narrowing the set of trainable parameters, enabling fine-tuning to occur on far less powerful hardware than would otherwise be required. This in turn shortens training time, allowing researchers to iterate quickly, test hypotheses, and deploy customized models without waiting weeks for retraining cycles to finish. Second, it slashes storage requirements. Instead of saving a full copy of a model for every specialized task, organizations need only store the small LoRa modules, which are lightweight and portable. Third, LoRa allows practitioners to preserve the integrity of the base model. The original pre-trained weights remain frozen and unchanged, meaning they can be reused indefinitely for different fine-tuning projects. Together, these advantages explain why LoRa has been adopted across academia and industry. It is not merely an optimization trick, but a paradigm shift that makes fine-tuning scalable, modular, and far more inclusive. Adapters offer another pathway to parameter-efficient tuning, though they approach the problem differently than LoRa. Instead of adding low-rank matrices into existing weights, adapters insert small, trainable modules between the frozen layers of the model. These modules act like additional processing steps, learning to capture the nuances required for a specific task. When an input flows through the model, it passes not only through the frozen base layers, but also through the adapters, which apply their specialized adjustments. The appeal of adapters lies in their modularity. Multiple adapters can be trained for different tasks and swapped in and out of the same base model as needed. For example, one adapter might specialize in summarization, another in translation, and a third in sentiment analysis. Activating the appropriate adapter turns the general model into a task-specific expert without retraining the whole system. This modular approach makes adapters especially powerful in multitask environments where flexibility is more valuable than raw efficiency. The advantages of adapters extend beyond multitask switching. Because each adapter is self-contained, organizations can build libraries of adapters for different applications and share them without distributing entire base models. This enables collaboration across teams and even across institutions, since the adapters are lightweight and easy to exchange. It also simplifies maintenance. When new data becomes available or a task shifts in scope, only the relevant adapter needs retraining, not the entire model. Adapters are also useful for organizations with limited compute budgets, since training these small modules demands far less hardware than retraining full models. While they may introduce some latency because the input must pass through extra modules, this cost is generally small compared to the flexibility gained. Adapters therefore complement LoRa by providing modularity and task switching capabilities, making them an important part of the parameter-efficient tuning toolkit. Quantized LoRa, or QLORA, represents a further leap in efficiency by combining the principles of LoRa with quantization. Quantization reduces the precision of numbers used to represent model weights, often from 16 or 32-bit floating point values to 8-bit or even 4-bit integers. This reduction saves memory and computational power, allowing very large models to be fine-tuned on hardware that would normally be incapable of handling them. QLORA applies LoRa updates to a quantized version of the base model, achieving both low-rank adaptation and precision reduction. The result is an approach that brings the costs of fine-tuning down to levels accessible on consumer-grade hardware, such as laptops or single GPU servers. QLORA has been particularly transformative in the open-source community, where developers often lack access to high-end clusters but still want to experiment with large language models. It has made fine-tuning models with billions of parameters feasible in settings that previously would have been excluded. To understand quantization, picture a high-resolution photograph being stored in a compressed format. The fine details may be slightly reduced, but the overall picture remains recognizable and useful, with the added advantage that the file now takes up far less storage space. In the same way, quantization reduces the precision of the model's weights, introducing small approximations that slightly reduce accuracy but yield enormous savings in memory and speed. When combined with LoRa, which already reduces the number of trainable parameters, The two strategies reinforce one another to create a remarkably efficient process. QLORA has therefore become a cornerstone of parameter-efficient tuning, balancing the trade-off between performance and efficiency in a way that maximizes accessibility. Like all efficiency methods, QLORA involves trade-offs. The reduced precision of quantized weights can, in some cases, lead to small drops in accuracy compared to full fine-tuning or even standard LoRa. These drops are often negligible in practice, especially when weighed against the ability to run large models on modest hardware. However, for high-stakes applications, even minor performance reductions may matter, making it essential to evaluate carefully before deployment. Another trade-off is that quantization may not be equally effective across all model architectures, meaning QLORA must sometimes be adapted or tuned for specific systems. Still, the balance of efficiency and practicality makes it one of the most promising advances for scaling fine-tuning in ways that are sustainable and broadly accessible. The use cases for parameter-efficient tuning methods are wide-ranging. Healthcare organizations can adapt general models to medical contexts, training them with specialized literature and clinical notes to provide decision support. Law firms can fine-tune models with legal documents and case histories to build assistants that analyze contracts and precedents. Customer service departments can adapt models for product-specific queries, improving response accuracy without needing to maintain multiple large models. Finance companies can specialize models in regulatory compliance, fraud detection, or portfolio analysis, ensuring they capture the domain-specific language and reasoning patterns of their industry. In all of these cases, parameter-efficient tuning makes it possible to customize frontier-scale models to niche tasks without prohibitive costs, expanding the reach of AI into specialized professional domains. The scalability advantages of parameter-efficient tuning go beyond cost savings. By reducing the barriers to fine-tuning, these methods empower smaller teams, startups, and academic researchers to experiment with large models. Instead of requiring clusters of cutting-edge GPUs, fine-tuning can be performed on consumer-grade hardware or cloud instances with modest specifications. This democratizes AI development, ensuring that innovation is not monopolized by a few wealthy organizations. It allows for a diversity of voices and ideas in how models are applied, encouraging experimentation across cultures, industries, and research agendas. This inclusivity strengthens the AI ecosystem, as more participants can contribute to and benefit from advancements in language models. Parameter-efficient tuning is therefore not only a technical breakthrough, but also a social and economic one, broadening access to advanced AI capabilities. Research adoption of LoRa and QLORA has been rapid. Academic groups have embraced these methods as a way to explore model behavior without incurring unsustainable costs, while open-source communities have adopted them to share fine-tuned models across domains. Industry projects likewise use LoRa and QLORA to adapt general-purpose models into domain specialists without maintaining multiple heavyweight versions. This widespread adoption has created momentum, leading to refinements, extensions, and variations that continue to improve efficiency and usability. The speed of adoption suggests that parameter-efficient tuning is not just a temporary workaround, but a foundational technique in the future of AI development. When comparing LoRa, adapters, and QLORA, each method offers distinct strengths. LoRa excels at efficient, task-specific adaptation, balancing performance and cost. Adapters shine in multitask flexibility, allowing a single base model to support multiple domains with modular add-ons. QLORA pushes the efficiency frontier further, combining quantization with low-rank adaptation to bring fine-tuning into reach for modest hardware environments. These methods are not mutually exclusive. Many organizations combine them to maximize benefits, such as using adapters for multi-task switching on a LoRa-tuned base, or applying QLORA in resource-constrained deployments. Together, they form a toolkit of complementary strategies that make fine-tuning scalable, flexible, and accessible across contexts. Parameter-efficient tuning also sets the stage for broader model compression strategies. Just as LoRa, adapters, and QLORA reduce costs and storage for fine-tuning, techniques like pruning, knowledge distillation, and further quantization shrink models themselves for faster, lighter deployment. The connection is clear. Parameter-efficient tuning solves the challenge of adaptation, while compression solves the challenge of deployment. Together, they represent a continuum of efficiency-focused innovation that is making large-scale AI more practical, sustainable, and widely available. These synergies point toward a future where fine-tuning and compression are seamlessly integrated into model development pipelines, ensuring that advanced AI is not only powerful, but also efficient and accessible. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. One of the most striking economic benefits of parameter-efficient tuning is its ability to lower the entry barrier for advanced model use. Training or fine-tuning large models has historically been the domain of technology giants and well-funded research labs, because the compute requirements and storage costs were beyond the reach of smaller organizations. Parameter-efficient methods change this equation dramatically. Instead of needing hundreds of GPUs and vast storage systems, organizations can adapt a general-purpose model using relatively modest hardware and a fraction of the compute budget. This shift makes advanced AI accessible not only to mid-sized companies but also to startups, nonprofits, and academic groups. It transforms AI from a resource-intensive luxury into a more inclusive tool that many sectors can leverage. The economic implications ripple outward: more experimentation, more applications, and more innovation at the edges of the field. When small organizations can afford to adapt models, they can create solutions tailored to their local contexts, industries, and cultural needs, rather than relying exclusively on generic systems produced by a few dominant players. The practical deployment advantages of parameter-efficient tuning are equally compelling. In traditional fine-tuning, every new task or domain required retraining the entire model, creating massive duplication of effort. With parameter-efficient methods, organizations can keep the original pre-trained model intact and deploy small, lightweight, fine-tuned modules that adapt it for specific use cases. This means that a company can host one base model and dozens of specialized modules, switching between them as needed. Deployment pipelines become more manageable because only the small adapter modules or LoRa updates need to be distributed, not the entire massive model. This modularity allows teams to update their systems quickly, experiment with new tasks, and roll out improvements incrementally without destabilizing existing deployments. For industries like healthcare or finance, where regulatory changes and data updates are constant, this ability to update in a modular fashion without retraining from scratch is a significant advantage. Multitask flexibility is one of the standout features of adapter-based approaches. Instead of training separate models for each task, an organization can train different adapters for each domain and plug them into the same base model as needed. For example, one adapter might be trained to generate medical summaries, another to analyze legal documents, and another to provide customer service responses. Switching between these capabilities requires no retraining or duplication of the base model, just activation of the relevant adapter. This flexibility makes parameter-efficient tuning especially appealing in enterprise environments where multiple applications must coexist. The approach mirrors how humans develop specialized skills. The same person can be a parent, a manager, and a volunteer, switching roles fluidly without changing their core identity. Similarly, a single base model can become a versatile tool, shifting tasks smoothly through adapters without losing its general capabilities. Resource-constrained environments particularly benefit from QLORA, which allows fine-tuning on consumer-grade hardware. Historically, adapting a large language model was only possible with access to high-end GPUs or specialized computing clusters. QLORA reduces the precision of the base model's weights and combines this with low-rank adaptation, making it feasible to fine-tune models with billions of parameters on machines that cost a few $1,000s rather than millions. This democratization of fine-tuning means that developers in smaller companies, universities, or even individual hobbyists can participate in advancing AI. They can create specialized models for local languages, industries, or cultural contexts that might otherwise be ignored by larger corporations. In many ways, QLORA represents the clearest example of how parameter-efficient tuning shifts the balance of power, allowing resource-limited actors to create meaningful contributions to the AI ecosystem. Benchmark results have consistently shown that parameter-efficient tuning methods often match, and in some cases nearly equal, the performance of full fine-tuning. Researchers have found that LoRa, adapters, and QLORA can achieve comparable accuracy across tasks like summarization, translation, and classification while using a fraction of the resources. This parity challenges the assumption that bigger always means better. In fact, the ability to get near full fine-tuning performance without retraining all parameters suggests that the knowledge embedded in pre-trained models is robust and general, needing only small nudges to adapt. For practitioners, this means they can trust parameter-efficient methods not as second-best compromises, but as first-class tools that deliver strong performance at lower cost. Benchmark parity has been one of the main drivers of adoption, convincing skeptics that efficiency does not necessarily mean sacrificing quality. Another advantage of parameter-efficient tuning is the preservation of the base model. When all parameters are retrained in full fine-tuning, the original pre-trained model is overwritten, and its general capabilities may be lost. Parameter-efficient methods, however, keep the base model frozen and intact, ensuring that its broad linguistic and reasoning skills remain available. The fine-tuning modifications are stored externally, in lightweight matrices or modules, which can be added or removed without altering the underlying system. This preservation is invaluable for organizations that rely on a stable, reliable foundation while still needing customization. It is similar to having a master copy of a document. Instead of editing it directly, you create annotations or appendices, leaving the original untouched. The ability to preserve the base model also facilitates compliance and auditing, since the unchanged pre-trained system can serve as a reference or fallback if specialized fine-tuning introduces errors or unexpected behavior. Open-source ecosystems have embraced parameter-efficient tuning with particular enthusiasm. Communities working with open-source models often lack access to the large-scale compute clusters of industry leaders, making LoRa, adapters, and QLORA indispensable tools. By lowering the cost of customization, these methods allow open-source developers to fine-tune models for local languages, niche domains, or innovative experiments. The results are frequently shared back with the community as small adapter files or LoRa modules, which others can use or build upon without downloading massive base models. This collaborative cycle accelerates progress, with incremental improvements rapidly propagating through the ecosystem. Open-source projects like Hugging Face have integrated support for parameter-efficient tuning directly into their libraries, reinforcing the importance of these methods as foundational tools for the community. In this sense, parameter-efficient tuning has not only changed how models are adapted, but also how collaboration and knowledge sharing occur in AI research. Another compelling advantage of parameter-efficient methods is their compatibility with preference optimization techniques such as RLHF or DPO. Fine-tuning a model to align with human preferences using full-scale reinforcement learning is prohibitively expensive for most organizations, but when combined with LoRa or QLORA, preference optimization becomes far more affordable. Instead of retraining the entire model with costly preference data, organizations can apply preference optimization only to the lightweight modules. This allows them to align models with human values, improve safety, and adjust tone without the massive overhead traditionally required. The combination of preference optimization with parameter-efficient tuning represents a convergence of efficiency and alignment, making it possible to build safe, helpful, and adaptable systems at scale. This integration is already visible in both research and industry, where lightweight fine-tuning and alignment strategies are increasingly intertwined. Maintenance benefits further highlight the appeal of parameter-efficient tuning. Because the updates are modular and lightweight, models can be adjusted continuously as new data, regulations, or user needs arise. For example, if a company introduces a new product line, it can train a small LoRa module to handle related queries without retraining the full system. If regulatory requirements change, a new adapter can be created to adjust the model's responses accordingly. This modularity makes updating models more agile and cost-effective, aligning with the dynamic pace of industries where knowledge and requirements evolve constantly. Maintenance becomes less about massive retraining cycles and more about incremental updates, reducing downtime and keeping systems responsive to real-world changes. Deployment scalability is another area where parameter-efficient methods excel. Instead of distributing entire fine-tuned models, organizations can share only the small modules, which are orders of magnitude smaller in size. This makes it feasible to distribute task-specific updates widely, whether across internal teams, partner organizations, or open-source communities. It also simplifies deployment in cloud environments, where bandwidth and storage are often limiting factors. For example, a global company could maintain one central base model and send out small adapters to regional offices, each tailored to local contexts and languages. This approach reduces logistical burdens and ensures that specialized capabilities can be shared quickly and cheaply without duplicating massive resources. Despite their strengths, parameter-efficient methods are not without risks and limitations. In certain edge cases, they may produce slightly lower performance than full fine-tuning, particularly for tasks that require deep structural changes in the model's representations. Some methods may also be less compatible with specific architectures, limiting their generalizability. Quantization in QLORA, for example, introduces small inaccuracies that may be acceptable in most contexts but problematic in high-stakes applications like medical decision support. Additionally, the reliance on frozen base models means that if the base itself has limitations or biases, these cannot be fully corrected through lightweight modules alone. Awareness of these constraints is essential, ensuring that organizations use parameter-efficient methods wisely and complement them with additional safeguards where necessary. Future research trends in parameter-efficient tuning point toward expanding these techniques to multimodal models and larger context windows. Researchers are exploring how LoRa, adapters, and QLORA can be applied not only to text but also to vision, audio, and video models. They are also experimenting with ways to extend efficiency into long context processing, where the challenge of scaling grows even more acute. Another direction is hybrid methods that combine multiple efficiency techniques, such as LoRa with pruning or adapters with distillation. These innovations aim to push the boundaries of efficiency further while maintaining or even improving performance. The trajectory suggests that parameter-efficient tuning will remain a vibrant research area, with continued refinements making large-scale AI more practical and adaptable across diverse applications. It is important to distinguish parameter-efficient tuning from model distillation, as the two are often conflated. Distillation reduces the size of a model by training a smaller model to mimic the outputs of a larger one, effectively shrinking the system for efficiency. Parameter-efficient tuning, by contrast, does not shrink the base model at all. Instead, it adapts the large model by training small add-on components while keeping the original weights intact. This means parameter-efficient tuning preserves the full capacity of the base model while layering task-specific skills on top. The distinction matters because it shows that these methods are not about making models smaller but about making adaptation cheaper and more modular. They complement, rather than replace, distillation in the broader landscape of efficiency strategies. The democratizing impact of parameter-efficient tuning cannot be overstated. By lowering costs, reducing resource requirements, and simplifying deployment, these methods broaden access to advanced AI technologies. They empower organizations that were previously excluded from the frontier of AI development to participate meaningfully, creating applications tailored to their unique needs and contexts. This democratization not only expands the reach of AI but also enriches its diversity, ensuring that the technology reflects a wider range of human perspectives and priorities. In many ways, parameter-efficient tuning embodies the ethos of inclusive innovation, turning what was once an exclusive capability into a shared resource. In conclusion, parameter-efficient tuning methods such as LoRa, adapters, and QLORA represent transformative innovations that make adapting large language models affordable, practical, and widely accessible. They reduce the need for full fine-tuning, preserve the integrity of base models, and enable modular updates that can be shared and maintained easily. Their compatibility with alignment techniques and their adoption across open-source and enterprise communities demonstrate their importance not only as efficiency tools but also as enablers of democratization. While not without trade-offs, their benefits far outweigh their limitations, making them central to the present and future of AI fine-tuning. These methods mark a shift in how models are trained, deployed, and shared, ensuring that the power of advanced AI is distributed more widely across society. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.